Hello, dear friend. Today we are discussing the chemical species assignment of the carbon peak. Carbon 1s. We commonly use adventitious carbon-carbon or organic carbon-carbon with binding energy around 284.8 for charge correction. After charge correction, we can proceed with the chemical identification of other elements. The adventitious carbon also has carbon-oxygen single bonds and carbon-oxygen double bonds. For the binding energy, the carbon-carbon or carbon-oxygen, the binding energy is around 285 as just mentioned. For the carbon-oxygen single bond, the binding energy is between 286 and 287. For the carbon-oxygen double bonds, the binding energy is between 288 and 289 electronvolt. Let's go to the XPS handbook. Take a look here, the energy distribution of different chemical states. The binding energy for the metal carbides is between 281 and 283. For inorganic carbon, such as graphite, the typical binding energy for the sp2 carbon is around 284, while for organic hydrocarbons, around 285, as just said. The binding energy of chemical bonds of carbon, nitrogen, carbon, sulfur, and carbon oxygen are between 285 and 288. With the increasing of electron negative elements, the binding energy shifts to a higher binding energy. For organic carbon fluorine, you can see the binding energy is quite high, generally exceeding 289 as the number of fluorine atoms increase, as in carbon fluorine 2, carbon fluorine 3, the corresponding binding energy also increases sequentially. You see, for carbon fluorine 3, it reaches around 293. So, with these references, we can attribute different chemical states to the carbon peak. Here are some references in the Advantage software. Quite detailed here. They're fixed ones, but actually we need to know that it represents an energy range. There are many examples of this. If the chemical structure has aromatic rings, it can result in satellite peak, pi satellite. You can see it is 6 electronvolt from the main peak. And the shape is short and broad with a higher peak width, just over 2 electronvolt. For inorganic carbon, inorganic graphite carbon, sp2 carbon is just the binding energy is around 284, while diamond-like sp3 carbon is around 285, with different peak widths. For sp2, the peak is narrow and asymmetric. You can see the tailing effect. just the peak half-width is around 1 electronvolt, while for sp3 carbon-carbon, the peak width is between 1.5 and 2 electronvolt, and sp2 carbon peak has a typical shake-up peak, is short and broad with a higher binding energy. For graphene, we should also know it has typical sp2 carbon bonding. The peak width is narrow, and the peak shape has an asymmetric tailing effect, along with a typical shake-up peak, plasmon loss features. Also, we can distinguish the diamond and graphite with the carbon KLL order peak. For the carbon carbides, metal carbides, and carbonates, we can see different binding energy. It's quite low. It's quite high. Such as calcium carbonates with carbon binding energy typically between 289 and 290. When we do peak analysis and perform peak fitting, the chemical states of carbon peak can be assigned based on these binding energies. Thank you for today.